My name is Amy Sullivan, and I'm the current immediate past president of AAAR. And it's my pleasure to welcome you to the 40th in our monthly AS&T lecture series. This is a new initiative being supported by the Freelander Memorial Fund. So each month, the editors of AS&T select a high-impact journal article to be presented by its authors. With these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us an opportunity to come together outside of the annual conference. These lectures are being recorded and will be later posted to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. In addition, each of these lectures is being hosted by one of our student chapters. So I want to thank everyone who's helped to make these possible and for all of you for joining us. And with that, I'll turn it over to our student chapter from the University of Illinois, Urbana-Champaign to get us started. Thanks.
Thank you so much, Amy, for inviting us to host this session. My name is Tahsina. I'm the current president of AAAR at UIUC chapter. And today I would like to welcome Dr. Edward Neal to present a lecture on novel methods for exploring the factors that govern particle resuspension. So Dr. Edward Neal is a postdoctoral researcher at the University of Bristol. He received an MPhil degree from the University of Manchester in 2020, where a master's project exploring lightning-induced pollen fragmentation sparked his interest in aerosol science. That's cool. He recently completed his PhD with the EPSRC Center for Doctoral Training in Aerosol Science, supervised by Professor Jonathan Reed at the University of Bristol, developing methods to examine non-ideal particle resuspension events. He now works as a postdoctoral researcher investigating single aerosol mass spectrometry techniques with Dr. Brian Busdek. Thank you so much, Edward, and let's start.
Lovely. Thank you so much to Tahsina and Amy for that introduction. So as mentioned, I'm going to be discussing some work for my PhD project. So this was looking at novel methods to explore particle resuspension. And in this lecture, I'm going to cover kind of work from two papers. So the first paper is the one that was probably sent out with the advertising for this lecture. So looking at developing a cost and space efficient method for particle resuspension studies. And then towards the end of this lecture, I'm going to discuss a paper that we've just had come out in AS&T as well. And that's really the follow-up to this method, looking at some of the applications of it, and specifically looking at non-ideal resuspension phenomena and taking some high temporal resolutions of that. So to give a bit of context to start off, in terms of why I'm interested in particle resuspension. And so particle resuspension is really a process that is happening kind of all around us all the time. So like any kind of movement can cause particles to be disturbed and be resuspended and transported back into the atmosphere. And so I've taken some stock images of various particle resuspension scenarios. So things like vehicles kicking up dust from road surfaces, cleaning in your house, particularly vacuuming, can resuspend particles. Doing exercise and kind of moving around will disrupt particles. And also you get kind of typical aeolian resuspension, so resuspension by wind. And so this can be important for like long-term transport of sand or microplastics and things like that. And really what I find interesting about particle resuspension is that it's governed by quite a complex mixture of factors. So the picture I have here is from a study by Wu et al., and they were looking at how a toddler crawling across different surfaces might resuspend different concentrations of particles. And although this is maybe quite a mundane, like regular daily life example, when you look into the specifics of that particle resuspension, it can depend on lots of factors. So things like relative humidity, particle size, how that toddler maybe is creating vibrations. Also things like the surface roughness of the rug and the material it's made out of. And one of the factors that I'm going to be concentrating mainly on today is also the morphology of the particles. So how different shapes may be resuspended differently and why some shapes may be left on that rug surface. And to give you a bit of a picture of the resuspension modeling landscape, so in terms of mechanistic models, so models that aren't too based on empirical measurements, we tend to focus on quite idealized scenarios. So if you look at this image on the left-hand side, so you've obviously got spherical particles, often hard, particles on kind of approximately smooth surfaces or surfaces that have a very specific amount of asperities on them. And so this is often the kind of ideal scenario that these models look at. And so one model in particular is called the rock and roll model that is often used when we think about mechanistic resuspension models. And in the rock and roll model, a particle is resuspended essentially by the aerodynamic forces creating a moment in one direction that will outcompete an adhesive force moment in the opposite direction. And that particle will rock across a pivot and eventually resuspend. And so there has, in previous years, been kind of an increasing complexity to some of these models. So this is an example from Goldestay et al., where they kind of mimicked surface roughness with hemispherical lumps on a particle surface. But still, it's obviously a bit more complex, but obviously not quite a real-world scenario. And so this was kind of the modeling landscape at the start of my PhD, kind of 5 years ago. Since then, we have had some models that have kind of produced some more interesting results. So things like this model from Villagran Olivares et al., where they were looking at kind of more complex kind of platelet-like particles. So this is kind of where the models are at the minute. But there is still some reliance on kind of empirical data in these models. And the idea at the start of my PhD was to take an idealized model. So this is a kind of method development that was proposed by Vincent et al. So you take an ideal model, you experimentally explore one real-world parameter. So you only focus on one of those factors. So they focused on relative humidity. You adapt the models to reflect that change. So here they've introduced a way to add kind of meniscuses to the resuspension model. And then you validate that model and repeat the whole process again. So the idea is that as you kind of like gradually cycle through this process, eventually you'll create a model that is both accurate and reliable, but also flexible to lots of different real-world scenarios. And kind of where my work and the work I was doing during my PhD resides is very much in this middle step here. So how do we experimentally explore resuspension to kind of guide the next steps of model development and also create kind of data sets to validate models against as well? And so when I started looking at developing a new method for looking at particle resuspension, I had certain requirements. So one of those requirements was based on the experiments we wanted to do. So we wanted to be able to control certain parameters of interest, but we also wanted to remove any other kind of unwanted real-world effects. So I'll come on to some of those real-world effects a bit later on, but they could be things like static adhesion coming into play, or maybe relative humidity effects as well. So we wanted to remove anything that could be influence our experiments without us knowing. I also was working at the time in a very multi-use laboratory environment. There wasn't loads of space available, so I needed something that was going to be quite small scale to be able to be used in that laboratory. And small scale can mean different things to different people. So, for example, this is a wind tunnel from 1978 where they referred to it as being portable because they could carry it around the country. But in reality, it's around about 6 meters long. So definitely wouldn't be appropriate for our kind of lab environment that we needed it for. And we also needed something that was fairly low cost. So I use the word relatively here because I appreciate low cost can mean different things in different scenarios, but something that was fairly low cost for my PhD student budget and also easy to construct. So these were the kind of goals I had in mind when starting this project. And what I came up with is this novel method for resuspension studies that kind of partners a method for fabricating particles with a 3D printed wind tunnel. So this here on the left-hand side is a quadrupole electrodynamic trap, and I refer to it often as the quadfab, so the quadrupole for controlled fabrication and deposition of particles. And this is a way of making particles like the SEM image here. And I then take those particles to a 3D printed wind tunnel. And so this wind tunnel is about 1 meter in size. All 3D printed materials, I'd use this wind tunnel to resuspend my particles. And I'm going to kind of go through each of these two methods that have been combined in turn. So in terms of the theory behind how we create the particles, so it really relies on this parameter called the Peclet number, so in this red box. here. So with the Peckley number, it's essentially just a ratio of the evaporation rate of a solvent from a droplet compared to the diffusion of the solute within a droplet. So as a droplet dries, obviously the solvent is evaporating. If that solvent is evaporating very quickly, so much more rapidly than the solute can diffuse within that droplet, you're going to end up with a surface enriched particle. And so that's the kind of particle that you see in this image here in D. So here you're in this sodium chloride particle was dried in a very dry relative humidity environment. So you end up with lots of nucleation sites on the surface of the particle and kind of a hollow center in the middle. And if you increase relative humidity, you end up with something quite different. So you end up with a particle that has just one nucleation site, this kind of flat bottom particle in the top images, A and B here. And so by just drying solution droplets in a controlled environment, you can reproducibly create different morphology particles. And here in Bristol, we've done this with various different materials and solutions. So here's another example where they were using polymer nanoparticles that were dispersed within a solution. And when dried, you kind of get these kind of quite funky looking particles with different size cavities depending on the relative humidity environment in which you dried those particles. And so with the quadfab, you dispense particles into the electric field controlled region. So these 4 cylindrical electrodes create an electric field and an area stability that runs down the center of a quadrupole trap. Those solution droplets evaporate their solvent away and they dry. And I'm catching those particles at the bottom of the quadfab here. So this breaking electrode has the same polarity as my droplets. And so I essentially form a queue of droplets towards the base of this quadrupole that are kind of waiting to be deposited on a surface below the instrument. And so this surface is on a motorized translation stage, so I can control exactly where those particles deposit. And by slowly reducing the breaking electrode voltage, I can deposit just a small number of particles at each kind of point on the surface. And to kind of show how that works in practice, so this is me trying to deposit particles in one straight line. So you can see that you kind of get 2 to 3 particles depositing with every deposition. I then move the slide along and I create more and more deposition sites. I got a bit more adventurous. I tried to write my initials. So this is EN in sodium chloride particles. And so you can see that we do have fairly fine control of particle deposition with this quadfab device. I would then create these samples of fairly reproducible morphology particles and take them to a 3D printed wind tunnel. So this wind tunnel is around about 1 meter in length, as I said. And essentially when creating the wind tunnel, we just wanted to have all the same capabilities of a normal wind tunnel, just a lot smaller. So the airflow going in is from a compressed air tank. It flows from a mass flow controller that controls the flow. So we have 100 liters per minute of air going in. The air then enters a kind of larger region, which is called the settling chamber. And this is the region we use for flow conditioning. So within the center of this region, we have lots of honeycomb lattices and ball bearings. And that is essentially there to laminarize our presumably slightly turbulent flow at this stage. So we create a laminar flow that is then going to be constricted and enter into the kind of smaller region of our wind tunnel. And although we have just created laminar flow, we then immediately create turbulence again. And the reason for this is we kind of want to have the same reproducible turbulence every single time we do an experiment. So on the walls of the wind tunnel in this region, we have a series of cones that the air interacts with and kind of stimulates a bit more turbulence to be added into the airflow. This is just reflecting kind of the airflow that particles would experience in the real world. So they'd experience a turbulent airflow, but they'd be small enough to kind of reside within the boundary layer of that flow. So they'll experience a laminar boundary layer flow, but that is being produced by turbulent airflow. And so that airflow is allowed to develop. So this long region here is just to ensure that that turbulence develops in a similar way every single time. And then that flow interacts with our particles on the base of the tunnel in this measurement region here. And so this is obviously a schematic drawn computationally. This is what it looked like in real life, maybe a little bit more bulldog clips and power fill. So this is the wind tunnel. It has obviously an optical setup as well to be able to image the particles. So we have a camera that points towards the base of our kind of glass slides. So we can monitor the number of particles that are on our surface. And then as the airflow interacts with those particles, we can monitor the number of particles that remain on the surface with time. We also have things like RH sensors, anemometers to measure the airflow as well. And so there were a series of kind of validation studies just to ensure that our wind tunnel was working as we expected it to. So I performed those studies with kind of different size spherical glass beads. And so this is what we see in a normal experiment. So if you follow the red dots on the slide here, you can see we can monitor at 100 frames per second a particle being detached from the surface and moving across our field of view. And if that particle exits the field of view, we kind of just assume it has been resuspended. I guess there's not really any way of us kind of knowing if that particle has resuspended or not, but we just assume that if it's traveled outside of the field of view, it will be resuspended. And from those images, we can then create a percentage resuspended plot with time. So this is for various sizes of glass standards, so from 25 micrometer diameter to just under 60 micrometers in diameter. And what was good is that we see what we expect. So we see the largest particles being resuspended most readily. So the 56 micrometer particles, the most easily resuspended. And what we also see is kind of two periods of resuspension. So as the flow is accelerating and first interacting with the particles, your most weakly adhered particles will be removed very quickly. So you get a whole bunch of particles removed in the very early stages of an experiment. But then what follows is resuspension that is a lot more gradual. And that's because those particles that are left are those that are most strongly adhered to the surface, and they'll need some kind of extra interaction in order to be released. So maybe like a turbulent eddy that breaks through to the surface to then provide the extra force to resuspend those particles. So it's a lot more gradual. So we kind of refer to like a rapid state of resuspension and a steady state of resuspension. And so even though the glass particles were working fine, we were seeing what we wanted to see. There were some other considerations we had to take into account. So one of them is collisions. So here I'm performing an experiment. If you follow the red particle, the red circled particle, it then interacts with another particle and causes that particle to resuspend as well. And we anticipate that collisions will be a very common way of particle resuspension occurring in the real world. But for our experiments, we kind of want to only focus on one parameter at a time. So we want to remove any likelihood of collisions taking place. And so we were able to kind of refine the amount of surface coverage of particles that you need in order to not see any collision events. And this is maybe one of the limitations with a smaller wind tunnel, is that obviously our field of view is fairly small, so it's about 80 millimeters by 80 millimeters. If you're then also having to constrain the surface coverage as well, you are having less and less particles that you're able to experiment on. We also looked at the flow within our wind tunnel. So we had a hot wire anemometer that had a very high temporal resolution, but we only had access to it for one day. And it's quite a delicate device. So we were able to kind of get an idea of some of the flow conditions within our wind tunnel and plot these kind of contour maps of both the flow velocity and also the turbulent kinetic energy. And we can use the turbulent kinetic energy to kind of get an estimate of the friction velocity, which is a kind of quite a common fluid dynamics parameter that are used in these resuspension studies. So we calculate our friction velocity, but obviously because it was only an estimate, we also tried to think about other ways where we could look at our friction velocity. So things like the Blasius equation, but also we had all these images of particles being resuspended, and we had particle velocity measurements. So we considered a way to take particle velocity measurements and kind of backtrack. So take the acceleration of that particle as it detaches, and using kind of force diagrams, kind of backtrack towards a friction velocity. And so that is what you see in this bottom plot here in plot C. So these individual points are kind of the friction velocity from particle velocity measurements. And as you can see, they kind of line up actually quite nicely with the Blasius equation and kind of give us a bit more confidence in our estimate for the actual friction velocity as well. So the final kind of unwanted influences that I thought I should talk about were both static effects, 3D printed resolution, and also a quick word on relative humidity. So with relative humidity, we were kind of putting our airflow through a dryer every single time we did an experiment. So that kind of reduced our relative humidity to below 30%. And really that is the relative humidity you need to be at to kind of reduce the likelihood of any kind of water or moisture bridges forming between a particle and the surface. We also looked at static effects. So with particle adhesion, you can have adhesion that is stimulated through electrostatics. And ideally, we wanted only the van der Waals adhesion to be present in our experiments. So we looked at we initially were using glass slides to do all our experiments. And then we moved towards using glass slides that were coated with indium tin oxide, so ITO coated surfaces. And what we saw was that actually there was quite a significant reduction in the resuspension efficiencies when performing experiments with the glass slides. And from our AFM measurements, it wasn't particularly, well, we couldn't really see that was due to any kind of roughness change particularly. So we put that down to the static effects kind of causing that difference between the glass and the ITO surfaces. We then also looked at the 3D printing resolution. So obviously it's not very common that wind tunnels are created by 3D printing. So you want to just double check whether the resolution of the 3D printer actually had any effect on our results. And what we saw was when using a finer resolution print, there was actually not really any change in our percentage resuspension measurements. So that was positive to see. So it means that you don't have to spend as long of your time 3D printing. And so with the wind tunnel validated, we actually wanted to then obviously look at non-spherical particles. So move away from these glass standards to sodium chloride particles dried in different relative humidity environments. So the two particles we looked at were sodium chloride dried in 0% relative humidity. So this is where you get the kind of multiple nucleation sites, what we refer to as kind of raspberry-shaped particles. So lots of little cubic structures with a hollow center. Then moving towards higher relative humidity particles, here we expect to see something like this middle image here. So like one nucleation site, kind of a flattish platelet-like particle. What we did tend to see sometimes at the higher relative humidity is another nucleation site. So you'd get the flat platelet-like particle, but maybe some other cubic structure on top of that as well. So there's maybe a little bit more variability when you went to the higher RHs. And what became apparent very quickly is that when trying to respend the sodium chloride particles in the wind tunnel is that we saw very little resuspension. So this is the glass standards on the left-hand side. And as we move towards doing experiments with sodium chloride, you can obviously see very quickly that not very much resuspension was recorded. And this was maybe somewhat expected because these sodium chloride particles, not spherical, but also are around 20 to 30 micrometers often in diameter. So they probably would, even if spherical, reside at the lower end of this plot here. And so with the wind tunnel as it was going to be very challenging to get kind of quantitative differences between these two particle types. And so we did a fairly simple fix, which was to double kind of the air compressor capacity of our wind tunnel. So we brought another air compressor attached to the wind tunnel and kind of gave us 2 tanks of airflow to play with. And this didn't quite double necessarily our velocity within the wind tunnel, but we got a bit more of an increase. So we're now looking at kind of 6 meters per second central tunnel velocity compared to 4.5 meters per second. And we did begin to see some difference between those two percentages of resuspension recorded. So at the 0% relative humidity, you got slightly higher resuspension than at 30%. And so as I say, although we're still very much at that low end of percentage resuspension, we are beginning to be able to see differences in the resuspension behavior of these two particles. But obviously, these are simply kind of numbers on a plot. We don't really know what are the actual reasons that these differences occur. So how are we actually going to be able to model these two different types of shapes and what should those models be focusing on. And so that's really where kind of the most recent ASNT paper kind of comes into play. Because we began to try and get some high time resolution imaging of particle detachment events. So this was an apparatus that has been used here in Bristol for a few years. So looking at high frame rate imaging of droplets depositing on surfaces, so looking at how they kind of wet surfaces or bounce off surfaces. And so it wasn't being used for a few months. So I took this apparatus and slightly adapted it by adding a jet air pump to the apparatus. And when I say jet air pump, it was simply a kind of bicycle tire pump that if you kind of pushed one pump of the bike pump, you got kind of an impinging jet airflow. And obviously this is a lot cruder than maybe the wind tunnel experiments we were doing, obviously a slightly more unpredictable airflow. But what we were hoping is to kind of monitor how these particles were detaching and monitor exactly what was happening at the very start of the incipient motion of these particles. So here on the right-hand side is some of the images that we started to collect. So you really can kind of monitor the particles at the very start of their resuspension lifetime. And we performed two types of experiments with this high frame rate apparatus. So one type of experiment was where we deposited particles with the quad fab in kind of one line across a surface. So we kind of tracked one line that could then be tracked with the high frame rate camera. So we took each of those particles and just imaged them. So it had quite a good optical resolution on the high frame rate camera. So we imaged each of the particles in that line in turn. And then I would pump one pump of the impinging jet airflow, and then I'd look back at the exact places where those particles were a second ago, and I'd record whether that particle had resuspended or not. So here is all the images of the 0% relative humidity sodium chloride particles that I had, and the ones coloured in green are the ones that were resuspended after they had one pump of the impinging jet interacted with them. And from all these images, I tried to kind of mine all the data I could out of them. So I looked at kind of particle height, the area of that particle if you draw a contour on the particle. I looked at the area of an enclosing circle around the particle. And I also tried to gauge an idea of the interaction between the particle and the surface. And so obviously all our images were kind of in just one plane. So it's obviously quite hard to garner what that surface interaction was. So what we did was we cropped the images kind of up to the point where the particle itself interacted with the reflection of the particle onto the surface. And we kind of defined that as, I guess, the area overlapping with the particle reflection, but as an area that was kind of analogous to surface contact. So obviously physically it's not surface contact, but we kind of want to see how that parameter impacted on the resuspension likelihood. And we plotted histograms of all these different surface or shape parameters. So if you go to that paper, there's, I think, 9 different shape parameters in each case. Ideally, we'd love to get more and more of these images so we kind of can increase the statistical significance of all the kind of trends we saw. In quite a lot of scenarios, so for example, like the circular diameter. This was circular diameter recorded for the 0% relative humidity particles. So these are the kind of like raspberry shaped particles. We would often see trends that somewhat appear a bit like the spherical scenario. So what you'd expect is a higher circular diameter, meaning more resuspension. And this is what we do kind of see, but then it's not kind of the complete trend. So there's obviously a bit more complexity to what is going on with these particles if you're just to think about circular diameter. And I think across the board, it was probably often not very wise to use parameters that were very specific to how circular a particle was or how spherical it was. They didn't tend to have very much trend with resuspension. What we did see more kind of association with was things like that percentage or like the surface contact area here recorded as a percentage. So when compared to the overall area of the particle, there's definitely a quite significant trend between the percentage surface contact area and the amount of particles being resuspended, or the likelihood of a particle being resuspended. So I guess what these two histograms here show is that for both 0% and the 30% relative humidity particles, having less seeming contact with the surface compared to the overall area of the particle would lead to more resuspension. But as I say, ideally we'd get more and more pictures of these detachment events to actually kind of confirm these ideas. And another factor that we were quite interested in was something called the Cori shape factor. So Kutapali and Novoselov a few years ago released a study where they did some experiments on I think they were RDX residue particles, and they recorded the Cori shape factor in all these cases. So they took images both from above the particle and kind of in view of the particle. And so they recorded the area of the particle from above and also the height of the particle. And the Cori shape factor is a ratio of the height compared to the square root of that area taken from above. And what they saw was quite a good dependence between that shape factor and the removal efficiency of those RDX residue particles. And again, we were only working in one plane, so we just did the best we could with what we had, where we used the height and then compared it to the area of the particle, actually kind of looking at it face on. But even with that definition of Cori shape factor, there definitely appeared to be some kind of relationship between Cori shape factor and the percentage of particles being resuspended. And so I do think as a method for kind of containing shape into one singular parameter, this would definitely be one to look at a bit more in the future. And then the second set of experiments that we performed were maybe somewhat the more funner experiments of kind of watching particle detachment actually take place. So with the high frame rate imaging, we could record images at 64,000 frames per second and actually monitor a particle be resuspended from the surface. So if you watch this video here, you see that particle lift up and begin rotating and eventually be resuspended. And if it was in the environment, it'd be resuspended back into the atmosphere. So we took various videos of various types of particles. So sodium chloride at 0% relative humidity, at 30% relative humidity, and then a few others, things like those polymer particles that I showed earlier on, and glass standard as well. And you can actually monitor the particle trajectory. So here in this plot, the blue points are the central points of the particle. So you can see that kind of takes the trajectory you would expect. So the particle kind of lifts up, and goes back and resuspend back into the atmosphere. But we can also monitor a point of interest. So if you watch this video here, we can track that red point on the edge of the particle as the particle rotates, and you kind of get some information about the actual rotation of the particle as well. And what we tried to garner from all this video information was what is actually happening when at the moment that particle detaches. So what is causing that particle to detach? And so the reason for this is that with spherical particles, what you expect to happen is that kind of rock and roll motion. So a particle will interact, or the drag force will interact with the particle. That drag force will lead to the particle rocking about a pivot point, and eventually it will break that pivot point and roll across the surface and eventually garner or gain enough momentum to resuspend back into the atmosphere. So that's the spherical case, but actually nobody really knows very much about whether that is still applicable to non-spherical particles. Would that actually be what happens in a non-spherical situation? And also there's not been any high frame rate imaging of non-spherical particles as far as we're aware in detachment scenarios. And so what we did is we took that point that we could track on the edge of the particle and our central particle position. We then worked out the angle between that central point and the point on the edge of the particle. And if you monitor that angle, you can monitor the rotation of the particle with time. And what happens in most cases, and what we were kind of expecting to happen, is that particle's rotation increases with time. So that angle will get bigger because that particle is rotating. And that kind of follows what you'd kind of expect from the rock and roll model in terms of it's a drag force that really influences particle resuspension opposed to the lift force. But then actually in some certain situations, we kind of saw a decrease of the angle right at the start of the detachment process. And what that was kind of saying to us was that if this angle here is decreasing, then maybe the height of the particle or the central point of the particle is being lifted up, whilst that edge point is kind of essentially staying in the same location. So maybe the edge of the particle is staying where it is, whilst the center of the particle is being raised. And you can see that on this plot here. So the difference in particle center height is plotted in the red, so that is increasing, but the angle from the center to the edge decreases slightly at the very start of this particle's kind of resuspension lifetime. And I think you can just about see it in this video here. So you see the particle lift up and then begin rotating. And this has some kind of important impacts for resuspension modeling. And so we didn't have loads of videos, so essentially it would be really important to take some more and really understand the kind of complex nature of particle detachment when you're not dealing with spherical particles anymore. But maybe actually the kind of rock and roll theory isn't as important for non-spherical particles, essentially. So could the lift force be playing more of a role than you see the lift force play when it's a spherical scenario? And in many cases, yes, you obviously see this rotation, so you see a bit of this rock motion going on. But the non-spherical particles don't really stay in contact with the surface for very long at all. They kind of quite rapidly kind of detach from the surface. And so it was only really as a scenario H where we did have some spherical particles where the particles kind of stay attached to the surface for a little bit and then begin resuspending. Whereas mostly the liftoff happens fairly instantaneously. And so linking back to kind of those wind tunnel measurements. So when we began to see this quantitative difference between those two particle morphologies, I guess with the high frame rate imaging, we set out to work out why those differences were happening, and also can we actually model those differences? The why is probably a little bit easier to answer. So seemingly from some of our results, there's definitely differences between surface contact area between those two particle types. There's definitely differences between the height of the particle that is exposed to the airflow. And I'm sure with more and more imaging of those events, we'd actually be able to hone in on those two factors being important. There also seems to be a lot of complexity when you actually start to look at the detachment mechanism. So I don't think it's as straightforward as the rock and roll method for non-spherical particles, although seemingly rotation is still a big part of particle resuspension. So maybe there is some difference between how these two particle types detach as well. And then the how I'm maybe going to slightly cop out of in terms of this is obviously a fairly experimental project, but as we look to the future of resuspension models, I think it would be useful to try and encompass shape maybe into one factor. So that Corey shape factor could be a good one to focus on. Definitely factors that focus on area in contact with the surface, but definitely some future work is needed, both experimentally and certainly from a modeling perspective on this. Kind of coming towards the end, but I did want to share a few other kind of fun detachment videos. So there were lots of detachments that maybe we weren't able to kind of quantitatively analyze, but did show some kind of fun events. So things like collisions happening between two spherical particles, two particles on top of each other, where the top one is being resuspended. And here on this right-hand side, you see this is one of our polymer particles, so it's probably a lot less dense than kind of the sodium chloride or the glass beads. And you kind of see it flap in the wind, so to speak, kind of flaps a little bit. So you do kind of see that rocking motion happening before it does eventually then get resuspended. So it would definitely be really beneficial to, I think, keep pursuing these high frame rate videos as a way to kind of gain more information about the detachment events. And so to conclude, we've in that first study, we kind of developed and validated a method to investigate non-ideal resuspension phenomena with the aim of improving mechanistic models in a kind of stepwise or gradual fashion. So I've now kind of finished on this project now, but I think there is a new PhD student starting at some point soon who will then kind of look at other parameters and hopefully gain some more of those videos and images of the particles as they resuspend. This is me here kind of first opening the new wind tunnel. It's a method that we believe is quite flexible to different kind of working scenarios. It's also fairly low cost and space efficient. So if other people want to kind of take up resuspension studies, it's very doable in kind of a benchtop scenario. There are a few shape parameters that we've now isolated that we'd like to kind of focus on more and definitely focus some of our modeling, any future modeling efforts on. And in terms of detachment mechanisms, it'll be interesting to see whether there are ways to vary the rock and roll model to incorporate maybe more direct liftoff events, for example. And with that, I want to say a massive thank you, particularly to lots of people here at the University of Bristol. So Jonathan Reed was my supervisor during this project. The people highlighted in red are some undergraduate project students who did lots or a fair amount of the measurements on this project. Also, this project was part funded by the Defence Science and Technology Laboratories here in the UK. So there's many scientists from DSTL who helped on this project as well. And kind of the whole Bristol Aerosol Research Centre being a very pleasant set of people to work with. And here in this bottom middle image, if you look really closely, it's BARC, so Bristol Aerosol Research Centre, kind of written out in deposited sodium chloride particles. And so thank you.
Thank you so much, Dr. Neil. That was an amazing presentation and very interesting topic of resuspension. So I would like to invite the audience to ask some questions. Please feel free to open your mic or comment if you have any questions, please go ahead.
Hi, Ed, it's Lauren.
Hi.
Did you synchronize the jet at all with the camera, the high frame rate camera?
No, it was very much like I was pumping the bike pump to
Right.
get the measurements. It was just like one pump, and I kind of essentially set up the experiment to focus on one particle. So yeah, there's a bit of kind of clicking stuff at the right time, but it would be a
Was
lot
that difficult to then find the frames that you were interested in?
It was a little bit, bit. So I remember now. Can't remember how I say it. I don't remember it being too difficult.
Okay. Maybe you just had some very large video files that you
Yes, that would
passed through. Yeah.
that would
Okay.
definitely be the case.
Yeah.
Yeah.
Okay. Thank you.
No worries.
So I think we have another question in the message section. So Abbas has texted, great talk, Dr. Neil. Thank you. How did you account for VDW adhesion? Any specific models in CFD for adhesion?
Oh, that's a good question. I'm not aware of specific models in CFD for adhesion for this experiment. I think there's some I guess I'm going to reference, there's like the Johnson-Kendall-Roberts way of working out van der Waals adhesion and also the DMT model of working out adhesion. Often so we did some AFM measurements to look at the adhesion between the tip and our surfaces. And often we found a little bit of discrepancy between kind of what you'd theoretically expect the adhesion to be from those models and our AFM results. And so I think adhesion is certainly an area of resuspension that is kind of ripe for research. I don't think there's very much knowledge on kind of real world surfaces and real world particles and what the adhesion is between them. But yeah, no, unfortunately, I don't know of any models, specifically or CFD models at least, for that.
I do have one question myself. So first of all, during your experimental setup, which part did you find to be the most like sensitive and the most challenging to control? Something that you might warn your new graduate student about?
Yes. I think one of the hard aspects for us was we weren't working with a very high flow rate. So often it was just challenging to observe resuspension, specifically for those non-spherical particles. If a new student was coming on board, I'd definitely say to just increase the flow rate. It solves so many problems. Because then you're working in a much more kind of quantitative region of those plots. So you're not working at 0 to 10%, you're working at kind of 10 to 90%. And be able to kind of quantitate those factors would be a lot easier. I think what would have been also nice to have done is that you can definitely do some very kind of intricate flow analysis. So if you had a really good hot wire anemometer, you can really get into what the flow is like at the point where those particles are interacting with the flow. We weren't able to do those measurements, but I think they would be really interesting to see kind of direct measurements of the flow in those regions. But also there's various CFD that we did try and do only in 2 dimensions. So maybe a 3D CFD would also be quite useful for this wind tunnel as well.
That's great. So that kind of links to my second question. So would you say the low flow rate was one of the major sources of uncertainty, or was there something else that can be considered like the most dominant source of uncertainty, at least in your experiments or your results?
Yes, I feel where I guess it's the uncertainty became quite a complex problem in terms of we were probably only with the lower flow rate, we were probably only releasing specifically for the non-spherical particles, maybe the most kind of weakly adhered particles. And so our adhesion of particles on the surface will be kind of like Gaussian distributed. So we were maybe only working with particles that were on one end of that distribution of adhesive forces, if that makes sense. So I think there would be variability in how those adhesive forces are working, and maybe a bit of a randomness that comes with working at that kind of lower end of the adhesive forces. And so, yeah, if we increase the flow rate, we'd probably be able to work at kind of I guess, the average adhesive force for our samples.
Interesting. Thank you so much. Do we have any more questions? We still have some time left. If you have any questions for our speaker, please feel free to open your mic, ask the question, or feel free to write it down. Okay, so we have 2 more questions. Salvatore is asking, how do you see this being used in non-wind tunnel or lab studies?
In non-wind tunnel lab studies. Interesting. As in, I guess what I would take for that question is maybe in terms of what is actually the use of doing lab studies and then take it to the models. Sorry, Salvatore.
So I'm mainly just asking if in a lab study we have a lot of control over all of these different variables, but if we're going to move out from using the lab study to then applying it to roadside aerosols and other kind of like indoor home studies. Like, do you see this being transferable to those type of studies, or is it kind of still like mainly just for these like lab?
Yeah, that's a good question. I guess the hope would be eventually those two kind of sets of studies eventually meet in the middle, if that makes sense. Like if we carry on doing this stepwise development and slowly increasing more and more complexity to our idealized lab studies, that eventually they'll meet what we see in those kind of more empirical or like more real world scenarios. I think there is, but I think it's probably a fair point that there's probably quite a big gap between those two situations. So there's probably quite a lot of work to do to get there. Like it would be nice to be able to model the kind of toddler crawling along across the surface, if that makes sense. But there's a lot of factors to think about.
Should I go to the next question?
Oh yeah, go for it.
Okay, I'm sorry if I'm pronouncing it wrong. Gady Minelis is asking, what was the smallest particle size you investigated?
Yes. So in terms of glass beads, it was 25 micrometers in diameter. And then for the sodium chloride, there was a bit more of a distribution of particle sizes, but it ranged from about 20 microns in diameter all the way up to kind of 40 or 50 micrometers in diameter. So there was, yeah, with the sodium chloride, there's probably a bit more of a distribution, kind of centered around 30 micrometers in diameter.
The next question is from Sarita. How do you distinguish lift-initiated detachment from rapid rocking, followed by lift in your observations?
Yeah, this is a very good question. I think it is something we discussed a lot is how do you rule out various kind of other detachment events. So I think at the temporal resolution that we were working with the kind of the plot that I was showing, that particle appears to almost rock backwards a little bit, opposed to in the direction of the airflow. And so because it did that, we kind of assumed like that goes against the idea that it's kind of starting to rock. But obviously, if the rocking is a lot more subtle or rapid than that, then we wouldn't be able to observe it in our experiments. I think it would be lovely to go to higher temporal resolutions and to kind of focus on more scenarios in order to get that kind of certainty that we need with different detachment mechanisms. But yeah, it's certainly definitely a good point. There's quite a lot to rule out as well.
Okay. I think we have 5 more minutes. So if you have any question, please feel free to ask. Maybe I can finish with one last question from myself. It's a bit of a, I think it's a bit of a out of reach question from the exact research you're doing. So I think in the beginning you were talking about microplastics and some possible applications of it. Can you probably like give us more insights into that and how it might be helpful in microplastics research?
Yeah, that's a good question. I think microplastics would definitely be one area that kind of future resuspension work could look into. So when I was writing my thesis, I kind of considered a bit in terms of like contextual stuff. So I think microplastics are obviously observed in very far corners of the world, and have obviously kind of been transported very long distances. I think, well, I believe that microplastics would kind of be a bit like sediment, obviously, where resuspension kind of forms part of that long range transport, but maybe kind of on the not quite as long range. So I think in terms of models for microplastic transport, you could start to incorporate resuspension, but just in a similar way to how you would with sediment, I believe. Just in view of how it gets transported over these kind of quite impressive distances.
That's interesting.
Um,
Thank you so much. So maybe if we don't have any more questions, maybe we can end this session. Amy?
Yes, thank you everyone for joining us. That was a great talk. Wonderful job hosting. I hope you all enjoyed it, and we'll see you all next month.